Hello everyone. In this video we are going to learn how to simulate asymmetric rolling process with the aid of the explicit solver of Abaqus using the 2D approach. As you may know, the difference between asymmetric rolling and the conventional rolling is that in asymmetric rolling we use different circumferential velocities on the upper and lower work rolls during the process. There are several ways to do that. For example, using work rolls with different diameters or different work roll velocities, or using a single roll, or forming with different lubricated work load surfaces. Now the question is why we use this process. Asymmetric rolling, or ASR, which is the abbreviation for it, ASR, is a technique to improve the formability of materials. In this technique, the natural line in the deformation cone is shifted compared to symmetric rolling. For more illustration, the point of the natural line at the slower work roll moves to the entry side, and the one at the faster work roll to the exit side of the deformation cone. Natural line is a vertical line that intersects with the point on the roll surface, at which the surface velocity of the roll and the workpiece are equal there. In the picture here you can see the natural line. Friction stress also generates additional shear strain throughout the thickness. As a result, this additional shear strain causes a change in the texture and microstructure of the rolled materials. But there is a problem in this process, which is bending the plate upwards and downward, generating a curvature throughout the length of the plate, which is called the ski effect. Here is the ski effect. Okay, after this brief introduction, we are going to simulate the deformation of an aluminum plate under asymmetric rolling process. By this simulation, we want to monitor and visualize the deformation behavior of the workpiece, besides the process forces which exerted on the rolls during the process. In addition to that, the amount of normal and shear strains and stresses which induced on the workpiece during the forming with the ASR process is the parameters that we want to monitor. Before going to the simulation environment, first let's review the process and tool design parameters as well as the four workpiece dimensions. As you can see in the picture, the workpiece is fixed from one side and the rolls move longitudinally towards the fixed side. They have different angular velocities, but the multiplication of angular velocity here to the radius of each of the rolls, here and here, reaches the same value. Regarding this, the rotational velocity of each is 2 times of the axial velocity here. It depends on your experiment or investigation conditions. Another important parameter is reduction ratio, which is the ratio of the final thickness of the plate to the initial one. Always refer to it with R. We assign 0.5 to this parameter. Other related parameters are shown in this table. We have also another table here that contains the stress strain data related to the aluminum workpiece which we want to deform during this simulation. Okay, now let's come to Abaqus environment. In the part module, we can create the workpiece and roles we need for the simulation. First, click on Create Part command, then enter aluminum, into the name field, select 2D, planar, deformable, and in the base feature select shell. Finally enter 0.1 for approximate size. Note that we use metric units in this simulation. We draw all the parts needed for the simulation in one sketch and then save it. So for creating other parts in the sketch section, we should just convert the redundant geometries into construction elements. First, we put a reference point at the center of the screen. Okay, then select Add Constraint button. We select Fixed and select the point and press Done. Okay, now the remaining parts. The radius of smaller row, I should put 0 and correct my table. Okay, as you see, I drew the parts and put them on the proper position. Now I just convert unwanted geometries into construction elements and click on the Save a Sketch command here and enter. I can do multiple selection by holding the Shift key down. At the end, we finish the sketch by clicking on the Done button. Again, part into a smaller row. Okay. I click on Add Sketch, select the sketch and press Done, and as I mentioned earlier, I should convert the redundant geometries into construction. So I hold down the Shift key for selecting the redundant geometry, multiple geometries, and finally I click on that. Well, it was a problem here. I'm sorry. I should convert it to analytical rigid. Okay. So this problem that happens is because in analytical section, analytical geometries, we should use arcs less than 180 degrees. So we have to divide the sketch in 3 sections. Okay. And I use the arc command for draw the segments of my analytical rigid part. So note that for converting the constructed elements to the real ones, or vice versa, you can click on a little arrow just below the Onset Construction button here. Holding Shift key for selecting multiple geometries and press down. So now I can regenerate. I will turn it to analytical rigid. Okay. Well, this problem happens in this level of simulation. I delete this and do it again properly. Smaller row, analytical rigid. This was the section that I forgotten. The remaining are the same as I told you. Done. I select redundant geometries and convert them to construction. As I told you, in analytical rigid surfaces, which are rolls in this simulation, the arcs cannot be bigger than 180 degrees. So for a full circle, we should divide them into 3 sections. So for this, I draw 3 arcs, each near 120 degrees. Converting construction geometries and yes, yeah. Okay, now we should repeat the same procedure for the bigger row. I just copy the previously made smaller roll and go to sketch environment and just change the sketch. Alright, at the end of the simulation, for regenerating, just right click on features and press regenerating to regenerate your parts. So parts are ready now, a workpiece and 2 rigid rolls. So we go in property module, we define the material properties and assign reference point to rigid parts. For this purpose, first I click on material, material manager window, then create. So here I change the name to aluminium. Under general density, as I mentioned earlier, we use metric units, 2,700 kilogram per cubic meter for density. Under mechanical tab, elasticity, elastic, Young modulus 70 gigapascal, and Poisson ratio around 0.33. Again, under mechanical tab, plasticity, then plastic. I copy paste the data that I have here detail section. Okay, because the units are metric, I should change the I should convert them to Pascal instead of megapascal. Okay, now I press OK, close the window. I click on create section, change the name to aluminium, solid, homogeneous, continue. I fill the checkbox and enter 20 centimeter as the width of the plate. Finally, I click on OK. Now I click on assign section. Alright. In this field, I click workpiece, assign section. I select workpiece and done. Yes. Okay, for each of the rigid part, we should define a reference point, which is the center of the arc. So I select each of them. And from Tools menu, I choose reference point. Then click on the center of the arc. Also here. In assembly module, we should bring in all the parts, then position them properly and assign set and surface to each of them to define boundary conditions and interactions. For doing this, I click on create part instances. I select all of them. And select independent, apply, and then I just close the window. And note that in this level we should define all the sets and surfaces which are needed. From tools menu under the set, and well, I'm sorry, these are remaining from the previous simulation. I delete them all. Set manager, also surface manager, so I delete them. To do it again. For example, for aluminium plate, if I want to assign a set, change the set name to aluminium, or yes, and I select the vertical line, then click on done. To define the surrounding surface of the workpiece, I should select multiple surfaces. So I use the shift button here, done. For each of the rows also I define the set on surfaces that are needed and name them properly. So let's do it again. Okay, in the case of rigid bodies, we should identify the side of the surface with the colors shown at the bottom of the page. Here I select magnetar because I want the outside surface. Here for bigger roll, I just copy it. I don't know if it is possible. In the step module, first click on create a step command. From the opening list, select dynamic explicit. Set the time to 5 seconds. In the mass scaling tab, choose the second option. Click on create, select set and choose aluminum plate, and in front of the scale by factor field enter 100 and finally click on OK. In step module, note that we specified the number and types of simulation levels and the outputs which expected to be the results of the simulation. Now from the output menu, under history output request, select manager, then in the edit, well, I should do it again. Okay, no problem. Create, continue. Here in front of interval, click type 200. Click on the arrow at the left of the energy and select internal and kinetic energy. These are internal and kinetic energy. For validation of the simulation, internal energy should remain under 10% of the kinetic energy during the simulation time. So I press OK. Also, in the history output manager window, again click on create, continue. In front of the domain field, select set, smaller row, click on the arrow at the left of the forces and reactions, also reaction forces, and select RF1 and RF2 to monitor the reaction forces in X and Y directions. Then press OK. Copy, yes, edit, adjust, change the set to bigger roll to do the same procedure, and for the bigger roll, and finally click on OK and close the window. Now we go in the interaction module, which we should define the friction between the surfaces. Create interaction surface, okay, create interaction, surface to surface, explicit, continue. Okay, here I should select the surfaces. First I select surface of the workpiece, again surface of the one of the rolls, and here if it is needed we should switch between the master and slave surface. Yes, the slave surface is the deformable one and the master surface is the rigid one. Here at the bottom of the window, press on the create interaction property, contact, continue, mechanical, tangential behavior, penalty, and type 0.15 for the friction coefficient, and select OK 2 times. So here, in the interaction manager, I just copy it and switch the surface for making the interaction of the workpiece surface and the smaller rigid rod. Then close the window. In the load module, we define boundary conditions. First, click on boundary condition manager, and create velocity, angular velocity, continue, aluminum, continue, check all the boxes, okay, create again velocity, angular velocity, smaller rule, continue, okay. Because the direction of the rotation of the smaller roll is clockwise, we should also enter a minus here. Again for the bigger roll. axial velocity and angular velocity, because it rotates counterclockwise, so the sign is positive. Okay. In the mesh module, we just mesh the workpiece. First, select part. Okay, because they are independent, we have chosen independent when we wanted to select them to the assembly environment, so it is no needed to come to part section. In assembly section also we can make sorry. Click on seed part, select the workpiece and enter 1 millimeter for the mesh size, and click on assign element, explicit, plane strain, and okay, and mesh the part. Well, as I told you, the analytical rigid parts didn't need to be meshed, so I come here in mesh part and leave them unmeshed. Finally, in the job module, to create a job, select job manager and create, continue, okay. To check that I insert the data correctly, click on data check and wait for the results. So now Abaqus is checking if I have inserted all the data correctly. Okay, as you can see, I have done this no problem for this simulation. Now I can press submit to start the simulation, but I have done this simulation before. Now for seeing the result, I'll just click on results to go to the visualization module. Here I can see the deformation behavior of the aluminum plate and also animated. Well, in the frame selector I do it faster. So ski effect also is apparent, and there are several parameters that you can monitor under the result menu. I can access to history output data, for example, and I select kinetic energy and internal energy, then plot, So you can see that the internal energy, yes, the kinetic energy is far beyond the 10% of the internal energy. So it shows that the simulation is valid. Also, you can plot the forces in X and Y directions. Here you can see the forces, and finally you can monitor the data, for example plastic strain or stress, and specify the type of data, Tresca or von Mises. Here, yes, and all the data that you have pre-selected in the step module. Okay, if you have any question, please write it in the comment section, and if you find this video helpful and want to see more videos like that, please give this video a thumbs up and subscribe to this channel. Thank you.